A colossal stone 3 times the weight of the Statue of Liberty lies abandoned in an Egyptian quarry. This is the Unfinished Obelisk, and it holds secrets that could rewrite our understanding of ancient history. By the end of our journey, you will possess a completely new lens through which to view humanity's technological past. We will examine impossible precision cuts and strange cylindrical holes that defy simple explanation. Could the builders of this monument have used tools far more advanced than we have ever credited them with? What does a civilization reveal about itself when it reaches for the impossible? The story is carved not just in stone, but in the very landscape of southern Egypt. To truly grasp the magnitude of the puzzle, we must stand where the ancient builders stood, in the granite quarries of Aswan. This was not merely a source of raw material, it was a vast open-air factory, an industrial complex under the endless desert sky. The bedrock here is a distinctive, rose-colored granite, prized across the ancient world for its stunning beauty and incredible strength. It was the premium building block for monuments meant to last for eternity, but that strength came at a cost. This granite is brutally hard, far tougher than the softer limestone used for many other structures. Working it with simple copper chisels and stone hammers would have been a task of almost unimaginable difficulty, a slow, grinding process that consumed tools and human energy at a staggering rate. Yet the pharaohs demanded it. They envisioned obelisks as towering needles of stone, piercing the heavens to honor the gods, and the quarry at Aswan shows us they thought on a scale that still takes our breath away. We are looking at the birthplace of giants. The floor of the quarry is the living bedrock itself, scoured and scarred by centuries of labor, and there, lying in its trench, is the unfinished obelisk, never separated from the earth that birthed it. Its intended size is the first colossal clue. This single piece of stone was meant to be over 1,200 tons. To put that in perspective, it is heavier than 2 fully loaded jumbo jets. Just the first question, before we even consider the intricate carving, is utterly daunting. How do you pry a block that size free without it shattering? How do you move it even an inch? The quarry floor offers hints of this massive logistics puzzle, with tracks and ramps that speak to a highly organized operation involving thousands. This setting transforms our mystery. We are not looking at a simple artistic endeavor. We are examining the footprint of a major state-sponsored industry, a project that would have consumed vast resources and required masterful engineering. The environment itself, the hard stone, the sheer scale of the intended product, the organized workspaces sets a very high bar for the technology that must have been employed. It tells us that whatever methods were used here, they were not primitive guesswork. They were the result of sophisticated knowledge passed down and refined. This is the stage, and the unfinished obelisk is the lead actor, frozen in mid-performance. And as we move closer to examine it, the first strange details begin to emerge from the stone, details that do not match the traditional story of hammer and chisel at all. 42 meters of solid granite. That is the ghostly outline of the obelisk, still etched into the quarry floor. To stand beside it is to feel a profound shift in perspective, a realization that the ancient builders were not just carving stone, they were attempting to redefine what was physically possible. This sheer scale is our first and most undeniable clue. It forces a simple, practical question. How do you work with a material this hard, on a project this vast, using tools we are told were essentially blunt instruments? The conventional explanation paints a picture of immense, grinding effort. Teams of workers would have pounded the granite with balls of Diorite, a stone even harder, using a technique called fire setting to weaken the rock with heat before dousing it with water to cause microfractures. Copper saws, aided by abrasive sand, would have been dragged back and forth for what must have felt like an eternity. On paper, these methods work. In a small-scale test, they can produce a cut. But scale changes everything. When you multiply that slow, arduous process across the surface area of a 1,200-ton monolith, the numbers begin to strain credibility. The time required, the number of copper saws that would have been worn to nothing, the sheer volume of abrasive sand needed, the logistical support for a workforce large enough to maintain constant hammering for generations, it all points to an effort of almost mythical proportions. The ambition we see here is not just artistic, it is industrial. It speaks to a command over materials and logistics that rivals modern mega projects. So we are left with two possibilities, both profound in their own way. Either ancient Egypt marshaled a concentration of human labor and endurance so vast, so sustained, that it pushes the boundaries of what we believe organized societies could achieve, or they possessed a technological edge, a method of working stone that was significantly more efficient than the hammer and chisel model we have long accepted. The scale of the obelisk does not quietly suggest this dilemma, it shouts it from the quarry floor. This monument was a statement, and perhaps part of that statement was a demonstration of mastery that we have simply forgotten. The trench surrounding the obelisk is a masterpiece of engineering in its own right. Carved deep into the unyielding granite, it forms a precise and startlingly straight channel that defines the entire shape of the monument. This was the crucial first cut, the incision meant to separate the dream from the earth. To stand in that trench today is to be surrounded by walls of smooth, rose-colored stone that rise higher than a person. Their surfaces are remarkably even, with a consistency that seems to whisper of a controlled process, not random pounding. The traditional explanation suggests workers used heavy stone balls to pulverize the granite along a marked line, painstakingly chipping down to create the trench. And while this method could eventually produce a channel, the precision and cleanliness observed here present a subtle but important challenge. Creating such straight, parallel walls over a distance of 42 meters, in stone this hard, with nothing but the swing of a hammer, introduces a significant margin for error. Each strike is a unique event, the angle and force slightly different, inevitably leading to a wavy, irregular surface over such a long run. Yet, the walls we see do not show that expected irregularity. They show a uniformity, a guiding line that was followed with extraordinary discipline. This consistency is the quiet heart of the mystery. It suggests the application of a guiding principle or a tool that could apply force in a repeatable, controlled manner. Some researchers looking at this have proposed a fascinating idea. What if the force was not just from a hammer's arc, but from a mechanical advantage? Could a heavy cutting blade, perhaps weighted or even mounted on a simple pivot, have been dragged back and forth along the guideline, using the abrasive sand we know they had, but with a consistency that human arms alone could not sustain? This is not to suggest a modern electric saw, but rather a forgotten intermediate technology, a powered motion that harnessed human or animal strength through levers or pulleys to create a repetitive cutting action. The trench, therefore, is more than a hole in the ground. It is a preserved snapshot of a technique, a fingerprint of the process. Its smooth walls stand as silent testimony against the idea of purely chaotic, manual bashing. They point toward a method that married immense power with delicate control, a signature of builders who understood their material intimately and possessed the ingenuity to tame it. And if this clue in the Grand Trench hints at a more sophisticated cutting method, then the next set of marks we find on the obelisk itself moves the mystery into even stranger territory. But the most compelling clues are often the smallest, scattered across the quarry floor and even along the trench of the obelisk itself are a series of strange, perfectly round holes. They look almost modern, as if someone took a giant power drill to the granite thousands of years ago, and in a way that is exactly what the evidence suggests happened. These are not random pits or cracks. They are deep, cylindrical borings with a consistent diameter, and their walls are often remarkably smooth and parallel. The official explanation is elegant in its simplicity. It is said that ancient workers used hollow copper tubes, loading them with abrasive quartz sand, and then spun them using a bow drill, a simple tool still used by carpenters today. The sand does the cutting, grinding away the granite as the tube rotates. In theory, this works, and for small projects like drilling a bead in a softer stone, it certainly did. But when we scale this process up to the holes we see at Aswan, the theory begins to wobble. Experiments with reconstructed bow drills on granite reveal a frustrating reality. Maintaining the high, steady rotational speed and the immense, consistent downward pressure needed to bore so deeply and so cleanly into this brutal stone is incredibly difficult with human power alone. The bow tends to wobble, the pressure fluctuates, and the result is usually a hole that is tapered, uneven, or much shallower than the ones preserved in the quarry. The holes at Aswan tell a different story. Their uniformity is the key. A perfectly cylindrical hole from top to bottom suggests a drill bit that did not waver. It suggests a rotation that was true and constant, and a feed pressure that was controlled and steady. This is less like a man struggling with a bow and more like the signature of a fixed apparatus, a tool mounted in a way that could apply relentless mechanical force. Think of the difference between hand sawing a piece of wood and using a table saw. Your hand can follow the line, but the table saw guarantees a perfectly straight cut because the blade is fixed and guided. The holes in the granite hint at a similar leap in technology. They point toward a drill that was stabilized, perhaps mounted on a frame or weighted with stones, and then turned by something more powerful and consistent than a single person's arm. Maybe a team using a capstan, or even a simple form of mechanical advantage we have yet to fully appreciate. These silent stone cylinders are not just holes, they are fossilized imprints of a process, the negative space left behind by a tool of significant capability. They force us to ask whether the ancient Egyptians had moved beyond the bow drill for their largest projects, inventing a form of powered machinery that has since been lost to time. And if they could drill with such precision, what else could they cut? The surface of the obelisk is a frozen diary of its creation. Etched into the granite are the final moments of work, a chaotic symphony of marks left by tools that fell silent. To the untrained eye, it might look like random damage, but to someone looking for a story, it is a detailed technical manuscript. On the underside, where the workers made their last cuts before abandoning the project, the evidence is most clear. Here we find two distinct languages written in stone. The first is familiar, the expected text of ancient quarrying. These are the rough, pitted scars, the jagged fractures and uneven surfaces that perfectly match the description of workers pounding the granite with heavy stone balls. This is the brute force method, leaving a signature of immense effort and controlled chaos. It is exactly what mainstream archaeology tells us they used. But right beside it, often intersecting it, is a second set of markings. These are different. They are long, linear grooves. They run straight for surprising distances. Their troughs are smoother, more uniform, with a regularity that feels intentional. They do not look like the aftermath of a hammer strike. They look like the path of a cut. This is where the quiet speculation begins. The pattern of these grooves suggests something other than impact. They hint at a tool that was drawn across the stone's surface, not just dropped onto it. A tool that moved. Could these be the tracks of a large, guided saw blade? Imagine a massive copper blade, perhaps set in a wooden frame, pulled back and forth by teams of workers. The abrasive sand, which we know they used, would be fed beneath it. The weight of the apparatus itself would provide the constant, steady pressure that a handheld tool could not. This would not be a power tool in our modern sense, but it would be a mechanized advantage, a way to convert human strength into a precise, repeatable cutting motion. The grooves on the obelisk, with their straight lines and consistent depth, fit this idea far better than they fit the idea of random pounding. They are the fossilized tracks of a process. To dismiss them as just another type of pounding mark is to ignore a subtle but crucial distinction in the evidence. It is the difference between chopping down a tree with an axe and cutting a board with a handsaw. Both require human effort, but one method allows for a level of precision and control the other cannot achieve. These grooves suggest the ancient masons were not just brute force sculptors, they were precision engineers. They had developed methods to guide their tools, to make them obey a line. This changes our entire perception of their capability. If they could cut such clean, straight channels into the hardest stone on Earth, what other feats of engineering might have been within their reach? The obelisk's surface does not give us easy answers, but it asks a profound question. Are we looking at one technology or two? The evidence implies a blend of methods, a sophisticated toolkit where the hammer and the guided saw worked side by side. This complexity itself is a clue. It points to a culture that was innovating, experimenting, and pushing the limits of the possible. And if that is true, then perhaps the greatest mystery is not the tool marks themselves, but why such an advanced technique seems to vanish from the historical record after this period. Freeing the stone from the earth was only the first impossible task. The real challenge began the moment it was loose. You now have a single block of granite weighing as much as 200 elephants, sitting at the bottom of a deep quarry trench. The next step, moving it, becomes a logistical puzzle of almost mythical proportions. The conventional explanation we are taught is one of sheer human muscle. The stone would be loaded onto a massive wooden sledge. This sledge would then be pulled along a prepared track, a roadway lubricated with water, or perhaps even a slurry of wet clay to reduce friction. This track would need to lead out of the quarry pit, up a constructed earthen ramp, across miles of desert, and finally to the banks of the Nile River, where it would be loaded onto a specially built barge. The manpower required is staggering. Some estimates suggest it would take well over 5,000 individuals just to get the sledge moving, all pulling in perfect, coordinated unison. The sound alone must have been deafening, a chorus of thousands of voices chanting to keep time, the groan of immense wooden beams, the grinding of stone on a wet track. It is an image of awe-inspiring collective effort, but when we examine this process step by step, practical questions emerge that strain the simple narrative. First, the ramp. Building an earthen ramp stable enough to support over 1,000 tons, with a gentle enough slope for men to pull from below, would be an enormous engineering project in itself, requiring the movement of more material than the obelisk. Then the sledge. Could any wooden structure, even the mightiest timbers from ancient Lebanon, withstand the concentrated pressure of that weight without simply crushing itself into the ground? The friction, even on a lubricated path, would be colossal, and the coordination, keeping thousands of pullers in sync to prevent catastrophic jerks or the sledge veering off its fragile track, borders on a miracle of crowd management. This is not to say it was impossible. Human ingenuity and endurance have achieved wonders, but the difficulty level is so astronomically high that it invites a deeper question. Could a civilization capable of cutting granite with such precision really have had no better solution for moving it than raw manpower? This is where the argument for more advanced tools finds a second, circumstantial pillar. Think of it this way: if the builders possessed a technology that made the cutting process significantly more efficient, a form of mechanized saw or drill, it suggests a mindset that sought out mechanical advantage. It reveals a culture of engineers who looked for smarter ways to solve physical problems. Would that same inventive spirit have stopped at the quarry's edge? It seems unlikely. Proponents of this view suggest that the same ingenuity applied to cutting might have been applied to moving. Perhaps they used systems of counterweights and levers to help lift the obelisk onto its sledge. Maybe they employed a more sophisticated form of roller or bearing than we have considered, something that reduced friction far more effectively than wet clay. Some even speculate about the use of vibrational techniques or harmonic forces, methods that sound like science fiction but are rooted in simple physics. We may never find a wooden machine preserved in the desert, but the sheer audacity of the transport problem, paired with the precision of the stonework, creates a compelling pattern. It paints a picture of a civilization not just throwing bodies at a problem, but mastering it through applied knowledge. The logistical nightmare of moving the unfinished obelisk, therefore, is more than just a story about ropes and sledges. It is a silent argument. It suggests that what we see as primitive brute force might have been the very last, most visible step in a process guided by a sophisticated and now forgotten understanding of mechanics. If they could make the stone obey their will in the cutting, why would they not also command its movement? The unfinished obelisk is a powerful piece of evidence, but it is not the only one. To understand if its strange marks represent a forgotten technology, we must look for a pattern, a signature repeated elsewhere. And ancient Egypt provides us with a gallery of such puzzles, each one echoing the same silent question. Travel north from Aswan to the Giza plateau, to the valley temple of the Pharaoh Khafre. Here you will find walls constructed from blocks of granite so massive they dwarf a person. But it is not their size that captivates engineers and historians, it is their fit. These colossal stones are joined together with seams of astonishing precision. In many places, the gap between multi-ton blocks is so minute you cannot slide a piece of paper between them. The surfaces are flat, perfectly planar over areas spanning several square meters. Creating such a surface with hand-held pounding stones is not just difficult, it verges on the geometrically improbable. Think of trying to flatten the top of a table using only a small rock. You might get it generally flat, but achieving a flawless, mirror-like plane across its entire surface would require a guiding principle, a reference standard. The stones at the Valley Temple suggest exactly that, a method for ensuring true flatness and perfect 90-degree corners that speaks of sophisticated metrology and control. Then there is the Serapeum of Saqqara, an underground labyrinth holding giant stone boxes. These are sarcophagi, but they are unlike any others. Carved from single blocks of granite or even harder diorite, they weigh up to 70 tons each. Their exteriors are smooth, but it is the interiors that defy belief. Inside, the surfaces are polished to a glass-like finish. The corners are not rounded from hand tooling, they are sharp, crisp, and perfectly square, meeting at precise right angles deep inside the stone. How do you achieve such a flawless interior corner in a material this hard with only a hammer and a chisel? You would need a tool small enough to fit into the corner, yet strong enough to cut the granite, and you would need to maintain that perfect geometry by feel alone in near darkness. The craftsmanship is so exact it looks machined, a word that makes archaeologists uncomfortable because it implies a technology we do not believe they had. Yet the evidence sits before us cool and silent in the underground chambers. When you place the unfinished obelisk beside these other artifacts, a compelling pattern emerges. It is a pattern of precision. At Aswan, we see the potential for guided cutting in the long, straight trenches and grooves. At Giza, we see the result of that precision in perfectly fitted mega blocks. At Saqqara, we see it refined to an art form in the mirror-like interiors of the stone boxes. This is not a collection of happy accidents or one-off miracles of craftsmanship. This is a consistent signature, a technological fingerprint found across different sites from different dynastic periods and applied to the hardest stones available. It points to a standardized knowledge, a school of stoneworking that understood how to achieve flatness, perpendicularity, and smoothness on a grand scale. The tools required to leave this signature, whatever their exact form, shared a common capability: the ability to apply controlled, repetitive motion to stone. They allowed the artisan to follow a line, to maintain a plane, to create a surface that was not just roughly shaped, but truly engineered. This pattern transforms the mystery. The question is no longer just about one abandoned obelisk in a quarry. It becomes a broader inquiry into the entire technological framework of ancient Egypt. Were these achievements the absolute pinnacle of what is possible with simple tools and superhuman effort? Or do they hint at a different toolbox altogether, one that has been lost to the sands of time, leaving only its perfect, polished products behind? But the story of forgotten tools does not begin with the pharaohs. To find its origins, we must venture even further back in time, into the shadowy era before the pyramids, before the first dynasties, before history as we know it even began. Here in pre-dynastic Egypt, we encounter objects that are quietly, profoundly baffling. They are the diorite bowls. Diorite is a volcanic stone, a dense, crystalline material that is significantly harder than granite. It ranks high on the Mohs scale of mineral hardness, a substance that would quickly destroy copper tools and resist even the hardest pounding stones. Yet from this unforgiving material, ancient artisans produced vessels of breathtaking delicacy. These are not crude cups, they are masterpieces of precision. Their walls are astonishingly thin and uniform. Their shapes are perfectly symmetrical, with flowing, graceful curves that turn in on themselves. Some even feature intricate fluting or decorative patterns etched into their sides with geometric consistency. To hold one is to hold a paradox. It feels impossibly heavy, yet looks impossibly delicate. The craftsmanship is so refined it seems to belong to a much later, more technologically advanced age. So how were they made? The standard explanation of grinding and polishing with abrasive sand is, on the surface, plausible. With enough time and patience, you can shape anything. But when we examine the specific challenges of these bowls, that explanation begins to feel incomplete. Creating such a thin, even wall from a solid block of diorite using only hand-held tools is a task of almost unimaginable difficulty. You would have to hollow out the center without cracking the sides, all while maintaining a perfect, symmetrical curve from lip to base. Any inconsistency in the pressure of your hand, any slight wobble in your grinding motion, would leave a telltale ripple or a weak spot in the wall. The bowls we have shown no such signs. Their symmetry is flawless. This level of control points to something beyond freehand grinding. It suggests a stabilizing principle, a method that removed the human hand's inherent tremor from the most critical part of the process. This is where a fascinating theory emerges from researchers who study ancient manufacturing. Could these bowls be evidence of an early, primitive lathe? The concept is elegantly simple. Imagine taking the block of diorite and mounting it on a spindle between two fixed points. Now, by using a cord or a simple foot pedal, you can rotate the stone block steadily. With a workpiece spinning, you then bring a fixed, sharp tool, a point of hardened copper or even a piece of flint loaded with abrasive, to bear against it. The spinning does the work. Your hand merely guides the tool, allowing for a consistency of cut that freehand work could never achieve. This is not a powered lathe in the industrial sense. It is a human-powered rotary apparatus, but that simple mechanical advantage, the conversion of reciprocal motion into smooth rotation, would be revolutionary. It would explain the perfect symmetry, the uniform wall thickness, and even the intricate fluting, which could be created by holding the tool steady as the bowl spins. If this theory holds, its implications are staggering. It means that a form of mechanized toolmaking was not a peak achievement of the Pyramid Age, but a foundational technology that existed centuries, even millennia before. These delicate diorite bowls become more than beautiful artifacts. They become the earliest fingerprints of a technological lineage, a secret thread of ingenuity that wove its way through Egyptian history. They suggest that the precision seen in the obelisks and the temple blocks was not a sudden invention, but the mature expression of a very old and sophisticated craft tradition. The bowls whisper that the roots of this forgotten knowledge run deeper into the past than we ever suspected, waiting in plain sight, polished to a mirror finish, daring us to understand how they were truly made. But what if the tool was not a machine at all, but a formula? Our search for ancient power tools has focused on mechanics, on the idea of gears, levers, and spinning blades. Yet there is another, more subtle path to consider, one that explores the very nature of the stone itself. Could the ancient masons have possessed a form of chemical or thermal knowledge that allowed them to soften granite, to make it temporarily pliable like clay? This idea moves the mystery from the workshop into the realm of forgotten material science. Imagine a substance, perhaps derived from a local plant or a mineral compound, that when applied to the granite surface, reacted with its crystalline structure. The theory suggests this agent might have weakened the bonds between the quartz and feldspar crystals, effectively lowering the stone's hardness for a period of time. During this window, the granite could be shaped, carved, or even molded with tools that would otherwise be useless against it. Once the chemical reaction subsided or was washed away, the stone would regain its full, legendary hardness, locking the new shape in place forever. There is no direct archaeological evidence, no labeled jars of granite softener found in the Aswan quarries. But the absence of proof is not proof of absence, especially for an organic compound that would have decayed to nothing over millennia. The concept, however, is powerful because it reframes our entire definition of a power tool. We think of power as electricity or steam, but in its most fundamental sense, power is simply amplified human effort. A controlled chemical reaction that alters a material's property is absolutely a form of power. It is a tool as surely as a saw, but one made of knowledge rather than bronze. This line of thinking expands the possibilities exponentially. Perhaps the long, smooth grooves on the unfinished obelisk were not cut with a saw, but were instead traced with a heated rod or a trough filled with a reactive paste, the stone yielding along a predetermined path. It could explain how they achieved such flawless interior surfaces in the sarcophagi at Saqqara, where physical tools would have struggled to reach. The thermal version of this theory is equally compelling. We know the Egyptians used fire setting in mining, heating stone with fire, and then dousing it with water to create thermal shock and fractures. But what if their control over heat was more refined? Could they have developed a method to uniformly heat a granite surface to a specific, critical temperature, just enough to make it workable without causing it to crack? This would require a profound understanding of the material's thermal properties, a kind of empirical science passed down through generations of master craftsmen. While these chemical and thermal theories remain speculative, their value is not in providing a definitive answer, but in challenging the boundaries of our imagination. They ask us to look beyond the idea of a toolbox filled only with physical objects. The greatest tool any civilization possesses is its accumulated knowledge. If the ancient Egyptians had discovered a way to temporarily defeat the hardness of their own building materials, that knowledge would have been more valuable than gold and more closely guarded than any royal tomb. Its loss would be complete, leaving behind only the impossible stones as a silent testament to a science we can no longer comprehend. This shifts the mystery from a question of what did they build to a deeper, more haunting question: what did they know? Granite is only part of the story. The true weight of the unfinished obelisk is not measured in tons but in meaning. To understand the extreme lengths taken, we must see these monuments as the ancient Egyptians did, not as inert stone but as living symbols. An obelisk was a petrified ray of sunlight, a frozen beam from the sun god Ra himself, captured and anchored to the earth. Its sharply pointed peak, often capped in electrum, a shimmering alloy of gold and silver, was designed to catch the first and last light of day, blazing like a beacon of divine presence. This was no simple act of architectural vanity. Erecting an obelisk was one of the most profound religious and political acts a pharaoh could undertake. It was a permanent declaration of a sacred covenant between the ruler, the gods, and the very cosmos. It said, "Here at this spot, heaven touches earth." This immense symbolic burden transformed the engineering challenge. Failure was not merely a practical setback or a waste of resources. It risked being a spiritual failure, a flaw in the connection to the divine. The technology used, therefore, had to be as flawless as humanly possible. It had to be worthy of the ambition. This context turns our mystery inside out. The pursuit of the most effective, most precise building methods was not just a matter of civic engineering. It was a sacred imperative. A pharaoh commissioning an obelisk was not simply ordering a big stone. He was initiating a ritual that required perfection. This would have driven innovation to its absolute limits. Craftsmen and engineers were not just laborers, they were priests of a sort, intermediaries translating a divine concept into physical form. Their tools and techniques became extensions of a religious vow. This makes the fate of the unfinished obelisk at Aswan especially poignant. That catastrophic crack running through its length was more than a geological flaw. In the eyes of its creators, it was a theological flaw. The stone was rendered spiritually imperfect, incapable of carrying its holy burden. Its abandonment was an act of reverence, not just frustration. They left it in the quarry as a silent testament to a standard that could not be compromised. This sacred drive for perfection helps explain the relentless pursuit of precision we see etched into granite across Egypt. When your work is a prayer set in stone, good enough is not an option. You must find a way to make the cut straight, the surface true, the angles perfect. This spiritual context reframes our entire investigation into their methods. Perhaps the so-called power tools we have been searching for, the guided saws, the stabilized drills, the lost chemical knowledge, were not just clever inventions. They may have been spiritual necessities, born from a culture that demanded the impossible from its artisans because the gods deserved nothing less. The quest to understand how they built these monuments becomes, in part, a quest to understand what they believed. So how do we test the theories against the stone itself? We turn to the modern field of experimental archaeology, where scholars and craftsmen roll up their sleeves to work granite the old-fashioned way. Their goal is not to prove a point, but to understand a process, to feel the resistance of the stone and measure the true cost in time and effort. Teams have reconstructed the tools we believe were available: copper saws without teeth, heavy Diorite hammers, and piles of abrasive quartz sand. They have then set to work on fresh blocks of granite, following the ancient methods as closely as possible. The results are both illuminating and deeply puzzling. The techniques do work in a basic sense. A copper blade dragged back and forth, fed with sand, will eventually cut through the granite. A Diorite pounder will, over many hours, fracture and shape the surface. But the word eventually carries a tremendous weight. The process is agonizingly slow. The copper saws wear down rapidly, requiring constant replacement or reforging. The sand must be continually replenished, and the workers must maintain an exhausting, rhythmic motion for days on end to achieve even a modest incision. More tellingly, the finishes left behind by these experimental efforts rarely match the pristine surfaces we see on artifacts like the Diorite bowls or the valley temple blocks. The experimental cuts are often wavier, less uniform. The pounded surfaces are rougher, lacking the controlled flatness. This gap between modern reconstruction and ancient artifact is where the mystery breathes. It suggests that while we may be using the right category of tools, we might be missing a critical element of the technique, a nuance of application or a supplemental process that transformed a slow, grueling chore into a more refined operation. Perhaps it was the specific type of sand, or the angle and stabilization of the saw, or a wet versus dry process. The experiments prove the methods are possible, but they also starkly reveal their extreme inefficiency. When you scale this inefficiency up to the level of an obelisk quarry or a pyramid's casing stones, the numbers become almost surreal. The workforce required, the mountains of copper needed, the generations of labor dedicated solely to the grinding cut of a single saw blade. It all paints a picture of such monumental effort that it challenges our understanding of ancient societal organization. These modern experiments, in their honest struggle with the stone, have done something profound. They have not closed the case on how it was done. Instead, they have widened the gap between what we can easily replicate and what the ancients clearly achieved. They push the mystery further into the spotlight, forcing us to ask whether we are still missing a piece of the puzzle, a lost ingredient in the recipe for working stone that turned difficult labor into a precise and manageable craft. That final, fateful crack is more than a flaw, it is a storyteller. The unfinished obelisk bears a massive fracture running through its length, a deep, irrevocable split in the granite that forced its creators to walk away. This was not a minor setback. It was a catastrophic failure that transformed a monument into a museum exhibit. But this very misfortune provides us with an invaluable gift, a cross-section of the work frozen in time. The crack reveals the internal stresses of the stone and the hidden progress of the tools, offering a forensic window into the moment everything stopped. To understand why it happened, we must think like the ancient engineers. They were performing a delicate operation, carving a 1,200-ton block free from the living bedrock. As they chiseled and cut deeper into the trench surrounding the obelisk, they were gradually releasing the immense pressure held within the granite. Stone, especially on this scale, is not a passive material. It has internal tensions, a memory of the forces that formed it deep within the earth. The process of quarrying is a careful negotiation with those forces. The builders were likely in the final, most critical phase, undercutting the massive block to separate it from the quarry floor. This is when the stone's own hidden weaknesses can betray you. A slight irregularity in the granite's crystal structure, an unseen fissure from millennia of geological pressure, could have been the starting point. As the supporting stone was removed, the obelisk's own colossal weight, now unevenly supported, would have exerted a new and terrible stress. The granite, pushed beyond its limit, gave way with a sound that must have echoed through the quarry like thunder. That crack was the sound of a dream breaking. From an engineering perspective, this disaster is incredibly revealing. It tells us the builders were operating at the absolute edge of the possible. They were not working with a large margin for error. The scale of their ambition left no room for the stone's imperfections. This crack is a testament to the immense forces they were managing, or attempting to manage. It also provides a unique physical record. Because the fracture runs deep, it exposes the interior walls of the trench and the underside of the obelisk. We can see, in a way we never could on a finished monument, how deep the cuts had progressed, the angle of the tool work, and the profile of the separation process. It is like having an archaeological dig site already opened for us, a slice through history. Studying this flaw allows modern researchers to analyze the fracture pattern, to calculate the points of maximum stress, and to better understand the precise stage of work when the failure occurred. This misfortune, therefore, adds a crucial layer to our investigation. The crack is not an end to the story, but a dramatic twist that reveals the high-stakes nature of the endeavor. It underscores that this was not a routine construction project. It was a monumental gamble with the very laws of physics. The silent, rose-colored giant in the quarry holds its failure in plain view, and in doing so, it teaches us more about the ambition and the peril of its creation than any perfect, finished monument ever could. The cracks in our understanding have grown too wide to ignore. When we follow the evidence from the quarry trenches to the polished bowls, a persistent question lingers in the air. If the standard tools and methods struggle to replicate what we see, where does that leave us? This is where we encounter the compelling and often misunderstood hypothesis of lost knowledge. It is a simple but profound idea. Perhaps the ancient Egyptians, or a culture that came before them, achieved a technological sophistication that has simply not survived in the archaeological record. This is not a call for mythical intervention or visitors from the stars. It is a sober look at the fragility of human knowledge itself. Civilizations rise and fall. Libraries burn. Master craftsmen take their secrets to their resting places. Entire schools of thought can vanish in the turmoil of a changing world, leaving behind only the most durable artifacts of their genius. Think of it like this: if our own civilization were to fade away, what would remain after 1,000 years? The skyscrapers of steel and glass would rust and crumble. Our digital archives would be unreadable ghosts, but a granite monument, a dam, or a carved stone foundation would still stand, silently testifying to a capability that future archaeologists might struggle to explain. The proponents of this view ask us to consider the unfinished obelisk in exactly that light. It is not an anomaly but a fossil. It is the preserved imprint of a higher level of technical understanding, frozen at the very moment of its application. The precision grooves, the cylindrical drill holes, the impossible symmetry of the diorite vessels, these are not mysteries because the ancients were primitive. They are mysteries because we are missing a chapter from their technical manual. The tools themselves may have been the key, and they may have been made of materials that destiny conspired to erase. Imagine a master saw blade set in a massive wooden frame, a complex apparatus of ropes, pulleys, and counterweights designed to guide a cut. Or consider a drill mechanism built from timber and cordage, capable of generating steady rotational force. These are inventions of wood and ingenuity, not metal and electricity. In the dry heat of the desert, wood can last for centuries, but over millennia it returns to dust. An entire technology built upon such organic materials could disappear completely, leaving behind only the stone it was used to shape. This idea extends beyond physical objects to the realm of applied knowledge. What if their greatest tool was a formula, a carefully guarded chemical compound, or a perfected thermal process, passed orally from master to apprentice? Such knowledge is even more fragile than wood. It lives only in the minds that hold it and the practices that enact it. A single generation of disruption, a period of great conflict or cultural shift, and that chain of transmission is broken forever. The knowledge evaporates. All that remains is the bewildering product. This perspective reframes our entire investigation. We are not looking for a missing tool in a museum drawer. We are searching for the ghost of a methodology, the echo of a process that once made the impossible seem routine. The lost knowledge hypothesis does not provide easy answers. Instead, it offers a different way to frame the questions. It asks us to humble ourselves before the evidence and to accept that human history may be filled with silent chapters, periods of brilliance that flickered and then went dark, leaving only their grandest, most permanent works to whisper of what was once known. The term power tool conjures images of buzzing electricity and spinning steel, but strip that concept down to its most fundamental principle, and you find something much more ancient and universal. At its core, a power tool is simply a device that amplifies human effort. It takes the limited strength of an arm and multiplies it, or it takes an irregular, tiring motion and makes it smooth and repeatable. This is the realm of mechanical advantage, a knowledge the ancients understood intimately. They were masters of the lever, the pulley, the inclined plane. So when we ask if they had power tools, we are not searching for anachronistic engines. We are asking if they applied these principles of amplification to the specific, brutal problem of cutting granite. Think of a simple bow drill used for starting a fire or drilling a small hole. One person pulls the bow back and forth, spinning a shaft. It works, but it is limited by that single person's stamina and consistency. Now scale that idea up. Imagine a drill shaft as thick as your arm, mounted horizontally on a sturdy wooden frame. Instead of a small bow, a large rope is wound around the shaft. Two teams of workers, perhaps 10 people on each side, pull this rope back and forth in a coordinated rhythm. Suddenly, you have a machine. It is human-powered, yes, but it is no longer a hand tool. The rotation is steadier, the pressure on the cutting head is immense and constant, driven by the weight of the apparatus itself. This is a plausible ancient power drill. It leaves the same kind of cylindrical hole as a hand drill, but with the uniformity and depth we see in the quarries. The evidence is not in a preserved wooden frame, which would have long ago turned to dust. The evidence is in the perfection of the hole itself. Now apply that same thinking to sawing. We know they used copper blades and abrasive sand, but holding a heavy copper sheet and dragging it back and forth across a 42-meter-long obelisk is a recipe for wavy, uneven cuts. So, what if the blade was not handheld? What if it was fixed within a massive wooden saw frame, like a giant version of a woodworker's frame saw? This frame could be suspended from an overhead structure or guided by tracks on the quarry floor. Teams of workers would pull it back and forth, their combined strength translated into a long, straight, controlled cutting motion. The weight of the frame ensures constant downward pressure. The guided tracks ensure the cut stays true. The abrasive sand does the actual cutting, but the machine provides the relentless, precise application of force. This transforms the process from a feat of endurance into a feat of engineering. It explains the long, straight grooves on the unfinished obelisk that look so unlike random pounding marks. Could they have gone further? What about harnessing natural forces directly? The Nile was the lifeblood of Egypt, and its current was a constant, untiring source of energy. While no evidence exists, it is fascinating to ponder whether the inventive minds that created shadufs for irrigation might have experimented with water wheels. A turning water wheel could, through a series of gears or cranks, convert the river's flow into the reciprocal motion needed to drive a saw or a drill. This would be a true ancient industrial machine, a power tool in every sense, using a natural force to automate the most grueling part of the work. The absence of physical remains for such a device is not proof it didn't exist. Complex wooden machinery rarely survives 4,000 years. Its only legacy might be the sheer volume and precision of the stonework it helped to create. By redefining power in this way, we move from a dead-end debate about electricity to a fertile field of possibility. We shift from asking, did they have our technology, to asking what brilliant, context-appropriate technology did they develop to solve their problem. The granite at Aswan demanded more than muscle. It demanded ingenuity. The precise, consistent marks left behind are the signature of controlled force, of a process that was mastered and repeated. They are the echoes of a technology that was perfectly suited to its time and its task, a technology of wood, rope, stone, and profound human cleverness, leaving behind only the stone it was designed to shape. The Nile was not just a source of life, it was a source of power. Flowing past the very quarries of Aswan, its relentless current represented an untiring force, a natural engine waiting to be harnessed. While no ancient Egyptian water wheel has ever been discovered at a quarry site, the absence of physical evidence does not erase the compelling logic of the idea. The principles of hydraulics were not a mystery to them. They used the Nile's annual flood to irrigate their fields with sophisticated canal systems, and they employed the shaduf, a simple counterweight lever, to lift water for irrigation. This proves they thought in terms of capturing and redirecting natural force. So, if they could use water to move earth and nourish crops, is it such a leap to consider they might have used it to move stone? Imagine a hypothetical scenario. A large wooden water wheel is constructed at a strategic point along a quarry canal fed by the Nile's current. As the wheel turns, its rotational energy could be transferred through a series of wooden gears or a crankshaft. This converted motion could then drive a long, reciprocal saw blade back and forth across a block of granite, or spin a heavy drill shaft with a consistency human muscles could never maintain. The river itself becomes the worker, providing the continuous, smooth power needed for those precise cuts and uniform drill holes. This would be the ultimate silent partner, a machine that never tired, operating day and night. Even without a full mechanical system, water's role was undoubtedly crucial in simpler yet equally vital ways. Using water as a lubricant and coolant during cutting operations would have been a transformative technological advantage. Dry cutting granite with abrasive sand would create immense destructive heat, quickly degrading copper tools and making the work unbearable. But a steady stream of water directed onto the cutting line would solve multiple problems at once. It would keep the tool and the stone cooler, reducing thermal stress and preventing cracks. It would wash away the ground stone powder, clearing the cutting path for fresh abrasive. And it would turn the sand and stone dust into a smooth, efficient slurry, enhancing the cutting action. This simple act of applying water transforms a grinding, chaotic process into a controlled, efficient one. It turns a difficult task into a manageable craft. This line of thinking encourages us to look at the entire environment as a toolkit. The builders of the obelisks were not working against their world, they were engineering solutions from it. They had granite, the hardest stone, they had quartz sand, a perfect abrasive, and they had the Nile providing transport, sustenance, and potentially motive power. The genius of their approach may have been in the synthesis, in combining these elemental resources with human ingenuity to achieve what each alone could not. The river's flow, therefore, is more than a geographical footnote. It is a character in the story, whether as a cool, clear stream aiding a saw's path, or as the driving force behind a forgotten wooden machine. The water of the Nile whispers of possibilities. It reminds us that the most profound technologies are often those that listen to the world around them, turning the whisper of a current into the shaping of eternity. The granite itself may hold a memory of vibration. Among the most speculative and captivating theories is the idea that sound itself could have been a tool. Modern physics tells us that acoustic resonance is a powerful force. Every material has a natural frequency at which it vibrates most easily. Apply a sound wave at that precise pitch with enough energy, and you can create a standing wave that stresses the material in predictable, even dramatic ways. Glass shatters when an opera singer hits the right note. Could a massive block of granite be persuaded to fracture along a desired line with a carefully tuned and amplified sound? The concept seems pulled from legend, yet it persists because it speaks to a different kind of knowledge. It asks us to consider energy not as something you hold in your hand, but as something you shape in the air. While there is no direct archaeological evidence of sonic devices in the quarries of Aswan, the absence of physical proof does not entirely silence the question. We must look to the cultural context. Many ancient traditions, from the myths of the pyramids to the stories of distant cultures, contain references to stones being moved or shaped by sound, by chanting, by the blast of a sacred horn. These are often dismissed as mere metaphor or mystical exaggeration. But what if they are distant echoes of a real, if poorly understood, principle? Perhaps the rhythmic chanting of thousands of workers was not just for coordination, but served a dual purpose, their unified voices creating a low-frequency vibration that subtly aided the cutting process, loosening the stone's grip on itself. This theory, while highly controversial, fundamentally challenges our definition of a tool. It expands the idea from a physical object that contacts the stone to an invisible field of energy that interacts with it. Could the power in their power tools have been vibrational, a harnessing of harmonic physics? This line of thinking does not require alien technology. It requires a profound, empirical observation of the natural world, a recognition that everything vibrates and that those vibrations can be harnessed. A culture that spent generations working stone would have developed an intimate, almost subconscious, understanding of its properties. They might have learned through trial and error that striking a block in a certain way with a certain rhythm produced a cleaner fracture. From there, the leap to using dedicated instruments, large drums, tuned pipes, or even the architecture of the quarry itself as a sound chamber, is a leap of imagination, but not necessarily of impossibility. It represents a path of technological development our own civilization largely bypassed in favor of mechanical and electrical solutions. So while we may never find an ancient sonic saw, the resonance theory serves a vital purpose. It pushes us to broaden our perspective. It reminds us that our ancestors' understanding of physics might have traveled down different, more subtle paths, exploring the interplay between matter and energy in ways that left no metal behind to rust, only stories that whisper of a forgotten harmony between human intention and the song of the stone. A technology capable of carving granite with such precision would have been a state secret of the highest order. This shifts our focus from the stone itself to the society that held it. If the tools were more advanced than simple hammers, then the knowledge to use them would have been incredibly specialized, not something taught to every laborer in the quarry. It points to the existence of a highly trained, elite class of artisans or engineer priests. These would have been the guardians of a sacred craft, their methods passed down through rigorous apprenticeships protected by tradition and perhaps even by royal decree. The ability to shape the bones of the earth was power, both spiritual and political, and that power would have been carefully controlled. The social structure surrounding the obelisks begins to look less like a massive gang of workers and more like a sophisticated research and development operation with master craftsmen at its core. This reimagining of the workforce changes everything. The traditional image is one of immense scale, of tens of thousands toiling under the sun, but a more efficient technology could have altered that dynamic profoundly. While many hands would still be needed for logistics, transport, and support, the core act of shaping the stone might have required far fewer but far more skilled individuals. Instead of an ocean of unskilled labor, we might be looking at a smaller, elite core of technicians, the ancient equivalent of engineers and machinists, supported by a larger group of assistants and laborers. This doesn't diminish the achievement, it refines it. It suggests a society that valued specialized knowledge and technical skill, investing in training and innovation to solve its greatest challenges. The economic implications are equally staggering. Developing, maintaining, and securing such advanced techniques would have demanded immense resources. It speaks to a state with not just wealth, but with remarkable organizational capacity. The investment in tool development, in the welfare and secrecy of a skilled class, in the procurement of special materials beyond just copper and sand, all point to a centralized authority with long-term vision and deep coffers. The pharaoh's workshop was not just a construction site, it was a think tank. Viewing the unfinished obelisk through this lens transforms it completely. It ceases to be just a failed construction project and becomes a potential fossil of a complex technological ecosystem. The crack that doomed it may have frozen in time not just the stone, but the hierarchy, the economy, and the intellectual ambition of a civilization. We are prompted to ask new questions. Who were these master builders? Where did they train? How were they compensated and honored? What happened to their knowledge when a project failed or a dynasty fell? This perspective challenges the textbook portrait of ancient Egypt as a society that achieved its wonders solely through brute force and limitless manpower. It suggests a parallel narrative, one of ingenuity, of protected innovation, and of a technological sophistication that wove itself into the very fabric of power and religion. The silent giant in the quarry, therefore, is not an argument for aliens or lost super-civilizations. It is an argument for taking ancient human ingenuity more seriously, for allowing that our ancestors may have found brilliant, context-specific solutions that we have yet to fully rediscover. The true scale of their achievement may be measured not in the tons of stone they moved, but in the depth of the knowledge they possessed and the society they built to nurture it. The granite silence is profound, but it does not speak for everyone. To build a complete picture, we must listen to the voices of those who study these stones for a living, the archaeologists and Egyptologists who form the backbone of mainstream scholarship. Their perspective is not one of mystery, but of meticulous, evidence-based reconstruction. They offer a powerful and compelling counterargument to the idea of lost machines, one grounded in the physical objects we have actually found. Their case is built on a simple, undeniable fact. After centuries of excavation, we have uncovered thousands of ancient Egyptian tools. We have saws, chisels, and drills. We have the Diorite pounding stones worn smooth from use. We have copper blades and heaps of quartz sand abrasive. What we have never found, not in a single tomb, workshop, or midden heap, is a component from a complex wooden saw frame, a gear from a water-powered apparatus, or a mechanism for a mechanical drill. There are no wall paintings in tombs showing such devices in operation. No hieratic texts describe their construction or use. This absence, scholars argue, is deafening. If such transformative technology existed, why would a culture that documented everything from grain harvest to sandal making leave not a single trace of its most important industrial secret? From this foundation, they construct an explanation of breathtaking human achievement. The precision we marvel at, they say, is not a signature of advanced machinery, but the hard-earned result of three factors working in concert. The first is time. We impose modern expectations of speed upon ancient projects that were conceived across the span of a pharaoh's reign, or even across generations. What seems impossibly slow to us was simply the pace of work. The second is skill. They propose the existence of master craftsmen whose lifetime of experience gave them an almost supernatural feel for the stone, an intuitive understanding of grain, fracture points, and the precise angle of a strike. The third and most critical is organization. The true wonder of ancient Egypt, in this view, was not a secret tool, but its unparalleled ability to mobilize, house, feed, and coordinate thousands of workers into a single, purpose-driven machine. The state provided the logistics, the master masons provided the technique, and time did the rest. Take the cylindrical drill holes, so often cited as evidence of machine-like precision. Mainstream experiments have successfully replicated them using exactly the tools we know they had. A hollow copper tube is mounted on a simple wooden spindle. Abrasive sand is poured in the cut. As the tube is turned, either by a bow or by hand, the sand embeds itself into the copper's edge, creating a grinding surface harder than the surrounding granite. With patient, steady rotation and downward pressure, the tube grinds its way down and the sand is continually replenished. The process is slow, but it works. The perfectly parallel walls of the hole are not a sign of a powered drill, but a natural consequence of the physics. The tube, spinning true, wears away the granite evenly along its entire circumference. The result is a clean, cylindrical core that can be snapped free. This is not speculation, it is demonstrable, repeatable craft. This perspective asks us to reframe our awe. It redirects admiration from the hypothetical to the human. The story becomes one of immense cultural will, of a society so dedicated to its gods and its king, that it could marshal the sustained effort of countless individuals over decades. The perfectly fitted stones of the Valley Temple are not evidence of a laser-like cutting tool, but of generations of stonemasons honing a craft to an art form, using simple wooden straight edges, string lines, and polished stone reference planes to check their work. The diorite bowls are masterpieces of the lapidary's art, shaped by endless hours of grinding with handheld stones and sand, their symmetry a testament to a master's unwavering hand and eye. In this light, the unfinished obelisk is the ultimate testament to that effort's scale and ambition, and its crack is a reminder of the very real, physical limits they faced. Engaging with this counterargument is not a defeat for curiosity, it is its necessary discipline. It grounds our investigation in the solid earth of the archaeological record, preventing our theories from floating entirely into the realm of fantasy. It forces us to acknowledge the staggering capability of organized human labor and refined traditional skill. Yet, even as we listen, the quiet questions persist. Does the sheer magnitude of the work, when calculated across all of Egypt's monumental sites, truly fit within a plausible timeline using only these methods? Does the absence of evidence for complex machinery definitively prove it never existed, or could it speak to the fragility of wood and the secrecy of a priestly guild? By honestly weighing both the powerful explanations of mainstream scholarship and the lingering anomalies in the stone, we do not close the case. We open a richer, more nuanced conversation about how a civilization could truly have reached for eternity, and what their silent, granite witnesses are still trying to tell us. The precision found in Egypt was not a solitary phenomenon. Across oceans and continents, other ancient builders left behind their own stone puzzles, monuments that whisper the same technical questions into the wind. High in the Andes, the fortress of Sacsayhuaman presents a wall of staggering complexity. Its stones are not simple blocks, but massive, irregular polygons, each one uniquely shaped to interlock with its neighbors in a dizzying, three-dimensional jigsaw. The joints between these multi-ton stones are so tight that, as in Egypt, not even a blade of grass can find purchase. The scale is different, the architectural style distinct, yet the signature is hauntingly familiar, an obsession with perfect fit and the mastery of hard stone. Far to the east, on a plateau in Lebanon, the Roman-era temple complex of Baalbek rests upon a foundation that predates it by millennia. Here lie the trilithon, 3 limestone blocks, each estimated to weigh around 800 tons. Their size alone is a statement that echoes Aswan, but it is their placement that deepens the mystery. They were moved into position and fitted with a precision that seems to defy the era's presumed capabilities. These are just 2 examples in a scattered global gallery, from Easter Island to the foundations of forgotten cities in Asia. Direct cultural links between these distant sites are highly improbable. The builders of Sacsayhuaman had no contact with the pharaoh's engineers, and the masons of ancient Baalbek worked centuries apart from both. This geographical and chronological separation makes the parallels all the more significant. What we may be witnessing is not the spread of a single technology, but the independent emergence of similar solutions to a universal human challenge. When a culture reaches a certain level of ambition, when it desires to build monuments that will defy time itself, it inevitably turns to the most durable material available, stone. And not just any stone, but the hardest, most challenging varieties: granite, andesite, basalt. These materials present a common set of problems: how to cut them, how to shape them with precision, and how to move them on a colossal scale. It seems that different civilizations, when faced with these identical physical constraints, may have walked similar paths of innovation. This perspective transforms the unfinished obelisk from an Egyptian artifact into a global reference point. Studying its trenches and tool marks is not an isolated exercise. It is like acquiring a decoder for a recurring pattern in human history. the obelisk provides a uniquely clear snapshot, a project frozen mid-process, offering clues that finished monuments often conceal. When we look at the polygonal walls of Peru or the foundational stones of Lebanon through the lens of Aswan, we are equipped with better questions. We stop asking just how they did it and start asking what specific techniques they might have shared in principle, if not in detail. Did the builders of Sacsayhuaman also discover the mechanical advantage of a guided cutting frame? Did the engineers at Baalbek develop their own form of mass logistics, perhaps using a different method to overcome friction? The shared signature of precision suggests that, independently, they each found a way to move beyond brute force. Conventional historical narratives, which often chart progress in a linear, connected fashion, struggle to account for this scattered pattern. It creates a map of human achievement with puzzling, brilliant flares of technical sophistication appearing in disconnected corners of the ancient world. This does not imply a lost global civilization or extraterrestrial guidance, but rather highlights the incredible inventive capacity of humanity when driven by powerful cultural or spiritual imperatives. The drive to build the eternal, to honor gods or ancestors with indestructible stone, appears to have been a catalyst that could trigger leaps in practical engineering across different societies. The unfinished obelisk, therefore, becomes a key piece in a much larger, still unfolding story. It challenges us to see these ancient sites not as separate mysteries, but as individual chapters in a collective human saga of overcoming material limits, a story written in a language of cut stone that we are still learning how to read. The stone has kept its secrets for millennia, but our tools for listening have changed. We are no longer limited to the human eye and a measuring tape. Today, a new kind of investigation is possible, one that uses the silent gaze of lasers and the unseen pulses of radar to interrogate the granite without ever touching it. This is the realm of high-resolution, three-dimensional laser scanning, photogrammetry, and ground-penetrating radar. Imagine creating a perfect digital twin of the unfinished obelisk, a model so precise it captures every chip, every groove, and every microscopic undulation on its vast surface. This is not a photograph, it is a data cloud, a map of reality composed of billions of individual points. With this model, researchers can perform analyses that were once pure fantasy. They can measure the depth and profile of a tool mark with an accuracy of less than a millimeter. They can calculate the exact angle of a cut, trace the path of a fracture through the stone, and even look beneath the surface to map hidden flaws and stresses that have lurked unseen since the day the obelisk was abandoned. The goal is to move beyond what we can see and into the realm of what the stone has recorded. A human eye might see a series of rough grooves, but a computational analysis of a three-dimensional scan could reveal something astonishing: a consistent spacing between those grooves, a rhythmic pattern that suggests the repetitive strike of a tool mounted on a fixed pivot or guided along a track. It could detect harmonic vibrations in the cut lines, subtle waveforms frozen in the stone that might hint at the resonant frequency of a specific cutting process. Most importantly, this technology can search for the signature of guidance. The difference between a hand-held pounder and a tool moving along a constrained path is a difference in consistency. A free swinging hammer leaves a chaotic, stochastic pattern. A guided blade, even one pulled by human hands, leaves a more uniform, statistically regular signature. Advanced pattern recognition software can sift through the scan data to find these fingerprints, looking for the mathematical ghost of the machine that made them. This approach represents a fundamental shift in the conversation. It moves us from the realm of speculation and anecdote into the rigorous world of data-driven forensic science. We are no longer just asking what might have been possible. We are collecting empirical evidence of what actually happened. Each striation, each drill hole, Each polished surface becomes a data point in a vast silent testimony. By applying the tools of modern engineering and materials science to this ancient problem, we have our best hope yet for new, concrete insights. We can begin to reverse engineer the process from its results, not from our assumptions. This technological lens does not promise to solve the mystery overnight, but it does promise to refine the questions. It allows us to test hypotheses with a new level of objectivity. Does the evidence in the stone statistically support the use of guided tools? Can we rule out certain methods based on the precise geometry of the marks left behind? The silent giant in the quarry may finally be ready to speak, not in a language of myth, but in the clear, unambiguous dialect of data. That final, catastrophic crack was a gift in disguise. A finished obelisk is a statement polished smooth, its surfaces gleaming in the sun, all evidence of the struggle to create it carefully erased. It is a closed book. But the unfinished obelisk is a book left wide open, its pages the raw, unedited granite. Every mistake, every correction, every experimental cut is preserved in startling detail. This was not meant to be seen. In the ancient world, the process was a secret, the messy reality of work hidden behind a facade of seamless perfection. The polished obelisk in a temple courtyard proclaimed divine order and pharaonic power. The cracked giant in the Aswan quarry reveals the human ingenuity, the trial and error, and the sheer gritty effort required to manufacture that illusion. Think of it as the difference between a master painter's final, framed masterpiece and their rough sketches, their paint-smeared palette, and the half-finished canvas on the easel. The masterpiece tells you what they achieved. The studio tells you how they thought. The unfinished obelisk is that studio. The long, straight grooves are not just marks, they are a craftsman's train of thought, a record of a tool's path. The cylindrical drill holes are not just holes, they are frozen moments of applied physics, showing us the angle, the pressure, the rotation. The rough, pounded areas beside the smooth ones show us a technology in transition, a blend of methods being used side by side. This artifact is a unique dialogue between the artisan and the stone, captured mid-conversation. Its ultimate value lies in this very incompleteness. Success hides its methods, failure exposes them. Because the workers walked away, they left behind a pristine archaeological laboratory. There is no later renovation to confuse the evidence, no later dynasty's additions to muddy the timeline. What we see is exactly what was happening the day the crack rang out through the quarry. This makes it arguably the single most important object in the world for understanding pharaonic mega-engineering. The obelisks that stand in Rome, Paris, or Istanbul are magnificent, but they are silent. They offer only the answer. The unfinished obelisk in Aswan gives us all the questions, written directly onto the stone in a language of fracture and intention. It is a time capsule, not of treasures but of technique, waiting for us to learn how to read its rugged, rose-colored pages. This single cracked stone compels us to rethink a fundamental story, the story of progress itself. For centuries, we have viewed human history as a steady, upward march, a linear climb from simple tools to complex machines, from primitive beginnings to our own sophisticated present. We place ourselves comfortably at the summit of this imagined mountain, looking back at the winding path below. But the evidence carved into the granite quarries of Egypt whispers a different narrative. It suggests the path of human ingenuity may not be a straight line at all, but something more like a spiral, or even a series of peaks and valleys. The unfinished obelisk does not represent a primitive attempt. It represents a breathtakingly advanced one, frozen at its moment of failure. Its existence, alongside the other impossible precision found across the ancient world, forces a humbling question. What if our timeline is missing entire chapters of technological sophistication? What if knowledge, even profound, complex knowledge, can be gained, perfected, and then utterly lost? This is the concept of a cyclical or punctuated progress, where civilizations reach extraordinary heights of understanding specific to their needs and environment, only to see that specialized knowledge fade away with them, leaving behind only the durable, bewildering artifacts. The master masons who planned the obelisk possessed a deep, working understanding of geology, mechanics, and material science that allowed them to even attempt such a feat. That specific school of applied engineering, that particular toolkit of techniques, may have vanished from the earth not because it was inferior, but because the cultural conditions that nurtured it, the specific pharaoh, the priestly guilds, the economic priorities changed or collapsed. The stone endures, but the living tradition that shaped it turns to dust. This perspective directly challenges a modern hubris, the quiet assumption that our current technological moment represents the absolute pinnacle of human cleverness. We look at the past through the lens of our own tools, our electricity, our silicon chips, and we unconsciously judge everything that came before as a step on the way to us. The obelisk asks us to set that lens aside. It asks us to consider that a different civilization, with a completely different set of priorities and a different relationship with its environment, might have developed a different kind of brilliance altogether. Their pinnacle might have been in stone, in harmony with natural forces, in logistical genius and sustained communal effort, achieving results that our own technology, for all its power, might struggle to replicate without similar vast resources and time. This is not about declaring the ancients superior, but about declaring them different and potentially more sophisticated in ways we have failed to measure. Embracing this possibility is an act of intellectual humility. It means admitting the archaeological record is full of silent gaps, that the absence of evidence for a machine is not definitive proof of its non-existence, especially when the product so strongly suggests its possibility. It opens the door to more creative, more inclusive interpretations of human history. It allows us to see our ancestors not as rough drafts of ourselves, but as fully realized innovators solving their own monumental problems. By accepting that we do not have all the answers about the quarries of Aswan, we grant ancient humanity a greater depth of capability. This, in turn, reframes our own place in the long human story. We are not the inevitable endpoint, but simply another peak in a range of mountains, one that may itself be lost to future generations who unearth our rusting steel and crumbling concrete. The true lesson of the unfinished obelisk may not be a blueprint for a forgotten tool, but a timeless reminder. Human knowledge is a fragile flame, and the winds of time can blow it out, leaving only the stone it once warmed. The scattered clues begin to align into a single, compelling picture. We are not searching for a single lost device, but for a forgotten system of engineering, a sophisticated interplay of force, knowledge, and material. From the straight grooves on the obelisk to the flawless bowls of pre-dynastic Egypt, a plausible scenario emerges, one that requires no alien intervention, only a profound reassessment of ancient ingenuity. Imagine the Aswan Quarry not as a chaotic construction site, but as a vast, open-air machine shop. At its heart is not a mystery box of impossible technology, but a culture of master engineers who had perfected the art of amplification. They took the simple machines we all know, the lever, the wedge, the inclined plane, the pulley, and scaled them up into industrial tools. The cylindrical drill holes that seem so machined could be the product of a mechanically augmented drill. Picture a large copper tube mounted on a sturdy wooden frame. A heavy stone weight provides steady downward pressure, but instead of a single worker laboriously spinning it with a bow, imagine a long rope coiled around the drill shaft. Two teams of workers, perhaps 10 or 20 people each, walk in opposite directions, pulling the rope to spin the shaft with a smooth, powerful rotation. This is a capstone drill, a human-powered machine that generates the consistent torque and pressure needed to bore cleanly into granite. The sand abrasive does the cutting, but the machine provides the relentless, unwavering force. It is a power tool powered by coordinated human effort. The long, straight trenches and grooves tell a similar story of guided force. The traditional copper saw, a simple sheet of metal, becomes something entirely different when it is mounted. Envision a massive wooden frame, like a giant version of a carpenter's frame saw, holding a long copper blade taut. This frame could be suspended from an overhead timber structure or guided by stone tracks laid on the quarry floor. Teams of pullers on either side draw the frame back and forth in a long, rhythmic stroke. The weight of the frame itself ensures constant contact, and the guided tracks force the cut to follow a perfectly straight line. Here, the abrasive slurry of sand and water becomes a cutting fluid, cooling the blade and efficiently grinding the stone. This transforms the act of sawing from a feat of endurance into a feat of precision engineering. The power is human, but the control is mechanical. This scenario synthesizes all the evidence. It explains the uniformity of the drill holes and the straightness of the cut marks. It accounts for the scale of the work by making it manageable through mechanical advantage, reducing the need for impossibly vast armies of laborers to a more plausible core of skilled technicians and coordinated teams. It embraces the empirical knowledge we know they possessed: the understanding of abrasive sands, the use of water as a lubricant, the keen observation of stone grain and fracture points. This is not a story of a secret, single invention. It is the story of a technological ecosystem. The ancient Egyptian master builders were system thinkers. They looked at the problem of granite and saw a solution that integrated multiple optimized processes. They had the quarry itself laid out for logistics. They had the Nile providing transport, water, and perhaps even motive force for some operations. They had a society organized to support long-term, state-sponsored projects. And they had generations of accumulated craft knowledge, allowing them to refine these compound machines to an extraordinary degree. The tragedy, and the source of our mystery, is that the most ingenious parts of this system were made of the most perishable materials. The massive wooden saw frames, the capstan drills, the complex rigging and scaffolding, all of it was constructed from timber and rope. In the dry Egyptian climate, wood might last centuries, but over millennia it returns to dust. Only the stone it was used to shape remains. We are left with the product and have had to infer the process from its flawless fingerprints. This evidence-based scenario does something important. It grants the ancient Egyptians the full credit of their engineering genius without resorting to the supernatural. It shows us a civilization that was every bit as innovative and clever as our own, but which directed its brilliance toward different ends, using the materials and physics available to them to achieve what we can only describe as monumental. Their power was not electrical, but it was very real, a symphony of leveraged human effort playing upon the hardest stone on Earth. The crack in the obelisk is also a crack in our timeline. We stand before it not just as tourists, but as detectives at a 4,000-year-old crime scene where the only witness is the stone itself. Its enduring power lies precisely in its refusal to give a single, simple answer. It does not proclaim a truth, it whispers a riddle. This taps into something fundamental within us, a deep-seated need to solve puzzles and to reconnect with worlds that have slipped through our fingers. The obelisk represents a tantalizing gap in the story we tell about human progress, a blank page in the middle of a book we thought we had read cover to cover. That gap is irresistible. Whether you are convinced by the arguments for advanced mechanical aids or you find the mainstream explanation of supreme skill and organization completely satisfying, the monument achieves something remarkable. It forces both sides to look deeper. It makes the believer in traditional tools confront the staggering scale of the achievement, and it makes the skeptic honestly weigh the anomalies in the stone. In doing so, it successfully accomplishes what all truly great monuments are meant to do. It is not merely something to look at, it is something to think with. It provokes wonder, ignites debate, and ensures that our understanding of the past is not a static museum exhibit, but a living, breathing conversation. This is its ultimate legacy. The unfinished obelisk is a physical question mark carved from rose-colored granite. Its value is not locked in a final answer about drill bits or saw blades. Its true power is its ability to keep our curiosity perpetually alive, to guarantee that the dialogue about our origins and our ancestors' capabilities never reaches a dull, settled conclusion. It reminds us that history is not a solved equation, but a continuous investigation. The monument is unfinished, and so, in the most beautiful way, is our quest to understand it. That eternal state of not knowing, of seeking, is perhaps the most human response of all, a tribute as enduring as the stone that inspires it. The rose-colored giant in the quarry does not give up its secrets easily. Our journey through the trenches and across its scarred surface reveals that this is no mere discarded stone. It is a profound historical cipher, a physical riddle left by a civilization at the height of its ambition. We have measured the impossible precision of its cuts, pondered the uniformity of its drill holes, and wrestled with the staggering logistics of its intended journey. We have placed it alongside the flawless bowls of a forgotten age and the perfectly fitted stones of distant temples, finding a recurring signature of mastery etched into the hardest materials on Earth. While a single, definitive blueprint for an ancient power tool may never be found, the cumulative weight of this evidence builds a compelling case. It suggests that our ancestors possessed a technological sophistication, a nuanced understanding of materials and mechanics that we are still striving to fully comprehend. Their genius may have expressed itself not in electricity or steel, but in amplified human ingenuity, in forgotten systems of levers, guided frames, and applied physics that turned immense challenges into manageable craft. This exploration ultimately reminds us that history is not a closed book with all the answers neatly printed in the final chapter. It is an ongoing excavation, a conversation with the past where every new piece of evidence can refine the questions we ask. The true value of the unfinished obelisk lies not in providing a final verdict, but in its relentless power to provoke wonder and critical thought. It stands as a permanent invitation to look at the ancient world with fresh, curious eyes, to question the narratives we have inherited, and to remain open to the profound capabilities of those who came before us. If this deep dive into ancient mysteries has sparked your curiosity, consider subscribing for more journeys that challenge the historical narrative. We would love to hear your own thoughts and theories about the obelisk's enduring secrets in the comments below. The conversation, much like the investigation into our shared past, is always continuing.